So this happened in the history of generative modeling research multiple times. That before the DC-GAN paper, GANs actually didn't work well. And before the latest diffusion models paper, the original diffusion model has all the mathematical formulations almost there, but it just didn't work very well. And we need people to figure out the recipe to train these models and scale. I think the paper we just announced exactly does that for consistency models.
Today we're talking with Yang Song. Yang currently leads the strategic explorations team at OpenAI and has been responsible for some of the most important, influential research in diffusion over the past several years. Today we're going to focus on three of the areas that he developed. First, we'll talk about score matching as a technique in diffusion and the history of that idea. Second, we'll talk about the SDE and ODE interpretations of diffusion, which really led to a unification of a lot of the research that happened before that. And then finally, we'll talk about consistency models. I think Yang's research is incredibly interesting because it both had major practical implications, faster inference, sort of more techniques for steering, but it also led to much richer theoretical understandings of what diffusion models are doing and how they work by making these deep analogies to physics and earlier research on energy-based models. Enjoy.
So I wanted to start back in 2019 when you published the first score matching paper. And the first question I want to ask is just what got you thinking about diffusion models at that time? During this time period, at least on the outside, I kind of perceive it as this GAN era where, sort of all the best results in image generation in particular were sort of GAN-based things during this period. There were some very impressive results, but there must have been something that made you decide that you wanted to work on diffusion models. Why are you working on that instead of GANs?
Yeah, so at that time, there are a few alternative approaches or image generation. As you said, GANs are very good examples, but I didn't like GANs because they are pretty hard to train and you need tons of tricks to make it work. And in the meanwhile, other approaches like VAEs, they are easier to train, but their samples look not as good as GANs. So I was hoping to find an approach that are both easy to train and can generate good samples. On one hand, I was looking at energy-based models because I believe energy-based models, they are like GANs, very easy to parameterize, very flexible neural network architectures. So they have lots of potential. They could possibly generate good samples. However, at that time, energy-based models are harder to train. So I was hoping to make them easy to train. I think that's why I started working on score matching. Score matching is an approach for training energy-based models without requiring lots of additional compute. So, but score matching, it was also a very old concept. I had to make score matching work first, and that's why I started working on this line of research. I don't think we knew about diffusion models at that time, even though diffusion models were published much longer before that. So it started from the direction of energy-based models, but eventually, when more papers came out, we realized the connection between them.
Yeah, so I sort of think for EBMs at the time, sort of classically, they were trained using these MCMC methods.
Yes.
And people came up with some tricks like contrastive divergence or things like that to try these divergences a little bit sooner. So why did you sort of have the intuition that like there must be a better way? Why sort of did you get away from these existing methods?
Yeah, so what is the issue with MCMC training? So as you mentioned, we have contrastive divergence already. The issue is sampling process, MCMC, is quite expensive, and we have to do this sampling for each training iteration. So collectively, the cost would be astronomical. So why I knew there could be a better approach for this, because at that time, there were techniques like kernelized starting discrepancy and also new score matching from a long time ago. And these approaches do not require sampling from the energy-based models at all. It's just people haven't demonstrated their power in training energy-based models. And to adapt these techniques to deep neural networks, we need to do several additional innovations, to do several additional engineering techniques. So I think focusing on these alternative approaches and doesn't require MCMC was a very natural choice for us.
And where did the idea for score matching itself come from? Is this an idea that you had been aware of already from your physics background? Was it something that you had countered in the literature? What did you come up with? How did you come up with that in particular?
So this is more like something I came across in literature, and it also has strong connections to contrastive divergence. The original author was score matching. He had collaboration with Geoff Hinton before, and they had a very nice track up. Connecting.
Brian Anderson, or is this?
This is Apple. Yeah. So he had collaboration with Geoff Hinton, wrote a paper on why score matching has connections with contrastive divergence. So if you're aware of that paper, that is very pretty natural to go along the direction of score match. And one very interesting part of the paper is that I think in acknowledgements, Apple mentioned that Geoff Hinton has involved heavily in this project, but he declined to be listed as an author on the paper because the paper contained too many mathematical formulas. So, yeah, so
On principle, he doesn't want to be overly associated with math.
yeah, Geoff Hinton didn't want the paper to have so many formulas, but even though he made lots of contributions.
I didn't know that. Well, you touched on this, but one thing that I thought was really interesting about the paper is that you spend the early section talking about why kind of the naive implementation of score matching doesn't work.
Yeah.
And it seems like there's some pretty serious problems. So, you mentioned training works very poorly in places where, sort of the actual data distribution is sort of very sparse. You have this dimensionality problem, actually maybe two, right? So like the data manifold is lower dimensionality than the embedding space, but also, to do backprop, you have to compute this full Jacobian of the score function, which is enormous. And so, I guess the question I want to ask is, I could imagine people kind of running into those roadblocks and saying, okay, cool, this was like a nice idea, but in practice, there are these reasons why it doesn't work. But you must have had some intuition that it ought to work, and there was sort of hope on the other side of these problems, and they were sort of worth pushing through.
Mm-hmm. I guess maybe because I was a fearless grad student, I didn't know too much about this. If I had been working on score matching for 5 years, then maybe I will feel a little bit more pessimistic about this. I think when I was working on this score matching idea, that was in 2018. I attended Clear 2018, and in the conference, had a conversation with Yasha. So Yasha not only did research on diffusion models, he also worked on score matching a long time ago, and he had generalized the score matching to formulations like minimum probability flow, all those things. And I was talking with him, hoping to get his insights about score matching, and he was basically trying to convince me to abandon this direction because he has been doing research in this direction for a long time, and he believes there are fundamental issues with score matching that will not be able to make large-scale neural network training work. I think lots of his arguments make a lot of sense.
Yeah.
But once you inject Gaussian noise and perturb your data with Gaussian noise, then do score matching, lots of his concerns will actually go away. Maybe it's just because I didn't think too much about all the difficulties, and I just feel score matching is such a neat, such a nice idea, very good mathematical intuition, very clever tricks to get rid of the difficulty of MCMC sampling. So it would be such a pity if we cannot make it work. I just persist it anyways.
You had the optimism. Do you, I didn't know that about Joshua. Do you remember any sort of specific worries?
Yeah, the worries are more like score matching focus too much on local structure rather than global global properties of the data distribution.
Yeah.
So this makes a lot of sense because we need MCMC sampling to estimate the so-called normalizing constant of the probability distribution. A normalizing constant is a property, is a global property for the data distribution. So how come score matching can get rid of this difficulty?
Yeah.
Because score matching only focuses on local things.
Yeah.
So that's can't be a free lunch, right?
Yeah.
And I think his criticism about score matching at that time made lots of sense. But luckily we can the Gaussian perturbation idea that alleviates some of these issues.
Well, rolling the clock forward a little bit, right after score matching, I think maybe a year or so later, you published this paper on this SDE and ODE interlocation. Well, maybe before getting into the surprises, because I think that paper has a couple of things that, at least to me, were very surprising. What motivated you to want to take this continuous time approach in the first place? We sort of had these discrete samplers that were working reasonably well. What motivated you to want to look at continuous time?
Yeah, so I think it's partially motivated by the DDPM paper. So after we worked on score-based models, we wrote 2 papers about it, and then Jonathan Ho published his excellent paper on DDPM. And we realized that there are some strong connections between these 2 type of approaches, and there should be a way to unify them. The formulation in DDPM cannot be applied to the large dynamic sampling stack of our score-based models. So to actually unify them, we would need to generalize everything to continuous time. At that time, I think Yasha first proposed the SDE formulation. It's a mathematical generalization of a discrete time diffusion models if you use infinite number of time steps. And I found the reverse SDE formulation and the ODE formulation, putting everything together, we can have a unified samplers and that connects the DDPM sampling and also score-based model sampling.
Got it. So it's sort of this desire to unify these 2 approaches.
Yeah.
And so maybe this sort of comes to the first big surprise to me from this paper, which is that, you write down the forward time SDE and it makes sense. And, immediately you think, well, the reverse time equation must be very complicated. Probably there's no closed form for it. It's just going to be some huge intractable thing. And then you show that, not only does it have this very nice closed functional form, but the main unknown parameter is exactly the sort of data gradient of the log of the data distribution, aka exactly the thing you're training on for the score matching. And so, was that a surprise to you? Where did that come from?
So I certainly didn't know this would happen. It came as a very pleasant surprise to me as well. Yasha and I both had physics background. We knew that if the forward process is a diffusion process, then the reverse process would also be diffusion. But at that time, the closed form for the reverse diffusion process, it's actually not well known to people. But since we already knew that the reverse process should also be an SDE, there must be a closed form solution, or at least there must be more mathematical formulas around that. I started searching in the literature, and eventually I found there was a paper from Australia in 70s last century actually wrote down the explicit formula for the reverse SDE. And I tried to do some straightforward derivations from their SDE formula, and eventually that gave us the very simple formula that involves the score function.
Yeah.
And once I saw the score function, I knew, well, now this is the right approach to unify score-based models and diffusion models.
That's super interesting. And it sounds like you sort of, the first paper came first, where you sort of came up with looking at the score function. And then it was a bit of a surprise that was actually sort of dropped out of this equation later. You didn't know that going in.
No, I didn't expect this would happen.
Yeah, so interesting. Well, to me, the second big surprise from that paper is that, so if we sort of take the first miracle for granted, you sort of write down the reverse time equation and it's this nice closed form. We have good SDE samplers, that might be enough by itself. But then you notice that you can actually write down a deterministic ODE, and the marginal probability distributions for that are exactly the same as the stochastic one.
Yeah.
And, now we can use all of this heady machinery that we have from ODEs over the years to work on reverse time sampling.
Yeah.
So how did that come about? Was that, again, I want to ask the same question. Was that something that you knew was going to happen, or was that also a surprise?
So I would say that was also a very pleasant surprise to us as well. Once we have written down the closed form of the reverse SDE, now it becomes possible to unify larger dynamics in score-based model sampling and also the DDPM sampling process. The very, very natural question is, can we generalize the sampling approach even further? And this could potentially give us better sampling algorithms. So the question is essentially how to sample from the marginal distributions of SDEs. And this question has been well studied in the SDE literature. And I think eventually I found its ODE formulation from previous paper in the field of SDE research. And the derivation was actually pretty straightforward. You can precisely write down the ODE formulation by considering the Fokker-Planck equation of the SDE. But the great thing of this ODE formulation that the previous paper didn't realize is you can actually compute the exact likelihood using this ODE. And this ODE also connects normalizing flows and neural ODEs with diffusion models. So I think it opens up lots of wonderful opportunities to improve diffusion model and to find the connections between diffusion models and all other different families of generative models.
Super interesting. This is a more kind of interpretive question, but to me, another thing that stands out about the score-based approach is that it has this really nice geometric intuition for a couple of things. So for example, for diffusion guidance, you write down Bayes' rule, you take logs, you take gradients, and then, it turns out that if you want to go in the direction of some sort of class label or some conditional information, you literally just add the relevant gradient and sort of like nudge the reverse process in that direction. What was sort of your reaction to that? Was that sort of a nice thing that fell out of this, or was that something that you noticed early on and was you excited about the?
Yeah. So that was actually part of the advantage of the score-based model formulation. So even before the SDE work, we knew that you can do this type of Bayesian inference with score-based models. And there have been research from UT Austin and applied score-based models for inverse problem solving. And you can view inverse problem solving basically the same as Bayesian inference, one certain type of guidance. So this all happened before the SD framework. And once we have written down the SD formulation, we found the score function again. And this immediately means we can do the same trick. We can do whatever trick we can apply for score functions and just use them for SDEs. Yeah. So then using this type of SD formulation for inverse problem solving, for guidance, for class conditional sampling, for text image generation, it's all become very natural. Yeah. I think when we were writing the SD paper, it was about the last week before the deadline. And Yasha was saying, okay, since now you have a very good formulation for conditional generation for inverse problem solving, why not apply this to text image generation? Yeah, so you can find a very good model that generates text from image. Now you can invert this model, and this will allow text image generation. I think that's definitely very ahead of the time. I guess we kind of already expected this to happen after this technique has been developed.
This is then like 2020, 2021?
Yeah, 2020.
Okay, yeah. And so this is literally a week before, just saying, hey, we should be able to do.
Yeah, we should be able to do it at that time.
I guess one last question on sort of the SDs and ODs is, one major plus of going in this direction is that we have really good ODE solvers.
Yeah.
And so, these have already been heavily optimized. In theory, they should sort of make sample generation much more efficient.
Yes.
Was that sort of a motivation for looking into this originally, or is that something that kind of came later and that you sort of noticed as a benefit of this approach?
Yeah, so this was not the original motivation for looking at the ODE formulation. I think at that time, my motivation for the ODE formulation is mostly how to compute the likelihood exactly. But once we can derive this ODE formulation and we generate samples with the ODEs, we noticed that the sampling speed is much faster. So we plotted the number of function evaluations in ODE solvers and found them to be much less compared to the typical sampling steps for diffusion models. And that came as a surprise to us as well. Yeah.
Well, maybe that's a good segue to consistency models, which, to me, again, from the outside, sort of start with this very surprising idea because um, sort of most diffusion models up until this point worked through this iterative reverse sampling process. And, I think in many cases, it was quite a lot of steps, like dozens of steps that people would go through to generate the results. And then consistency models sort of say, no, you don't have to do that. You can actually go in a single shot from the noisy image back to the sort of high resolution ones, the original data distribution. What was the intuition for why that should be possible? Did it come from kind of the neural ODE interpretation? Was there some other place that it came from? Why did you think that should even work in principle?
Right. So it came from the ODE interpretation. You can view consistency models as a learned ODE solver and solve the ODE in one step. And once we have the ODE, we know having a one-step solver is theoretically possible. It's just a matter of how to learn this solver. And that also made the idea of consistency models pretty straightforward. Yeah, following the ODE interpretation.
Got it. And then maybe this also leads to one of the approaches in that paper, which is sort of retrofitting existing diffusion models. So I think one thing that's nice is you sort of point out you can do this consistency distillation. You don't necessarily need to train a new model from scratch. Just come with a pre-existing diffusion model and we can turn it into a consistency model.
Yeah. So there are two main ideas in the consistency models paper. One idea, as you mentioned, is given a pre-trained diffusion model, we can fine-tune it to become a consistency model. So this saves a lot of compute and usually gives you better results. This approach is actually the more straightforward approach in this paper, because once we have written down the ODE given the pre-trained diffusion model, we can solve the ODE using a priori solvers and learn solvers in the form of consistency models will just be one option. The other idea in the consistency model paper, which I'm pretty proud of, is that you can actually train a consistency model from scratch and forget about everything related to diffusion models. So this makes consistency models a fully independent family of generative models. I think that came as a big surprise to all the co-authors. And so why this is important? Because for a long time, people were hoping to find a generative model that can do sampling in one step without requiring adversarial training. The only alternative is GANs. But we know GANs are hard to train and the training dynamics are complicated. For consistency models, it can also generate samples in one step, but it doesn't require adversarial training. So this is, I think, the only family of models that have this property, and it has very good sample quality comparable to GANs. So I feel this actually was a bigger progress compared to consistency distillation.
Well, one thing I love to ask sort of about the whole body of research, I sort of think something that's interesting about diffusion models is that they're a little bit more architecture agnostic in a way. And so, for a long time, people used UNets. I think like through your original score matching paper and also through DDPM. And those are both UNets, if I remember correctly.
Right.
And then, sort of later the people moved to these sort of cross-attention based and sort of closer to transformer architecture systems. But it seems like the method is quite general and maybe relatively architecture agnostic.
Right.
Do you have sort of some intuition about why that should be true, or, why you can get good results out of diffusion models in sort of a more architecture agnostic way?
Yeah. So I think one original motivation for developing score-based models and also diffusion models is we explicitly hope to make the method architecture agnostic. The reason is once we don't have strong constraints on the architectures, we have much bigger space exploring different architectures, and this also makes the possibility of finding a good architecture higher. So because the mathematical formulation allows these models to be architecture agnostic, I think it makes total sense for people to just try different architectures and keep those that work the best. Initially, we focused on UNets And this is like motivated by both theoretical insights and empirical findings. So as I mentioned, like score-based models initially was developed um, as an alternative to energy-based models, and they are gradients of energy-based models. If you assume the energy-based model is a coordinate, then the gradient will have a structure that is very similar to units. So that's one motivation we use the units. And also, at the time when I was working on a score-based model paper, I just tried numerous architectures. I took them from the computer vision literature. So this includes units, dilated convolution, lots of architectures used for uh, image segmentation tasks. And eventually I found unit just worked way better than everything else. And now people are switching to transformers.
Yeah.
And transformers work well and scale. But actually, if you compare the convergence speed of units and transformers, I would say units are still going to converge faster. It's just after enough training, transformer might have a bigger edge over units. Yeah, so I think units still have lots of advantages depending on the application, and transformers obviously better at larger scale.
Interesting. So what you might know an earlier paper than this, but I think of like the stable diffusion paper as the first one that sort of like made heavy use of this cross attention mechanism from the architecture. What was your reaction when, I guess, sort of seeing that paper, or what do you sort of think of as the first one that was more transformer inspired?
Yeah, so I think the stable diffusion paper didn't surprise me that much because they had a previous paper called Timing the Transformers. And these two papers have very similar ideas. The biggest difference is they replace the transformer in the latent space with the diffusion model in the latent space. So if I remember correctly, I think stable diffusion still uses a unit in the latent space. Maybe I'm wrong, but I think that was my impression. They are still using unit style structure, but the only difference is they train this model in the latent space instead of in the pixel space. I think there was a later paper called DIT. That paper was one of the earliest papers and investigated diffusion training with transformers. So I was not very surprised by this because I have done similar experiments before. Yeah, of course, scaling transformers with diffusion is a very straightforward idea, and people will definitely make it work. But I'm happy that we can now unify all the architectures with transformers. Yeah, stop worrying about how to design architectures more carefully.
Totally.
And yeah, it's great if we use transformer for diffusion, then it makes integration with transformer-based language models easier.
Yeah.
So that's definitely a very positive step in diffusion research.
As we're recording this, I published a new paper on sort of improved training for consistency models. What's the main idea or main ideas that you want people to take away from that paper?
I think maybe the main takeaway is now with consistency models, you can generate samples with very similar quality to the best diffusion models, but only using 2 sampling steps. So I think with consistency models, it's already possible to do real-time generation in lots of applications. And consistency models are also scalable approach, at least as scalable as diffusion models. So I would expect future research use more consistency models as an approach for faster sampling.
Mhm. And what the biggest belief update or biggest change since the original consistency models paper, as you sort of think about what led to that improvement?
Yeah, I think the biggest change is that we carefully updated everything and found a general approach to help train consistency models at large scale. So the mathematical formulation of consistency models, it hasn't changed much. It's already there for 2 years now.
Yeah.
But what's always more important is to find a set of recipe to make this approach actually work. So this happened in the history of generative modeling research multiple times. That before the DC-GAN paper, GANs actually didn't work well. And before the latest diffusion models paper, the original diffusion model has all the mathematical formulations almost there, but it just didn't work very well. And we need people to figure out the recipe to train these models at scale. I think the paper we just announced exactly does that for consistency models.
I think it's Sandra Dielman who has this riff on saying that we sort of have two different generative paradigms today. We sort of have this discrete token autoregressive paradigm inside of language modeling. And, then we have this sort of more continuous space feeling diffusion paradigm that we use for sort of most famously image generation, but also very important for even things that have time associated with them, even video generation and audio generation. What's sort of your prediction for the future of that? Do you think that we sort of end up in this two-tier world where we just keep these paradigms separate? Do you think there's any chance to unify them?
Yeah, I think we will definitely unify them. And even though they appear to be different, but at the core, they're actually the same approach. You can view autoregressive model as a special case of a diffusion model. And to some extent, you can also view diffusion models doing autoregressive generation in a latent space. So I really don't think there's so much separation between these two families of approaches. And bring both models under the same framework, it's not hard, and it's definitely going to happen for future large-scale multi-model generative models.
And you sort of have a feeling that this is sort of like the end of the approach for generative modeling, or is there something else yet to discover?
Yeah, I think this is definitely not the end, because autoregressive models or diffusion models, they have their own limitations. One example is the sampling speed. For language models, autoregressive generation is kind of slow. For diffusion models, image generation, video generation, they are also extremely slow. So there should be a better formulations of generative models that allow us to make the sampling process much faster. And consistency models are one possible approach.
Yeah.
That's why we work on it in the first place.
Yeah. This is very vague, and so I'm not sure if this, not sure exactly how I would frame this question, but it's sort of naively, it seems to me, in diffusion, there's sort of this interpretation that you figure out the lower frequencies first, and then you sort of go forward, you sort of go backwards in time, you're sort of adding higher and higher resolution, higher and higher frequency data to the image. Meanwhile, I sort of think in like the autoregressive next token prediction paradigm, it's not as obvious to me that something like that's happening. It sort of seems like each next token carries roughly the same amount of information as the one that came before it. There isn't such a sort of ordering of the process.
Right.
How do you think about that?
Yeah, so I think you have the right intuition. For autoregressive text generation, it's not going from low frequency to high frequency, and each token has roughly the same amount of information. I think this is precisely because language is developed by humans, and language on its own has much denser information compared to pixels in images. So humans also process languages more or less autoregressively. And languages are designed to be processed autoregressively in some sense. So that's why autoregressive generation on language is a very natural choice. For images, I think you can almost view the direction from low frequency to high frequency is one type of language for describing images. We always want to describe low frequency components of the image first, like what is the overall color of the image, what is the overall structure of the image, and then progressively move to higher frequency components. And diffusion does that implicitly. So from this perspective, it makes a lot of sense.
Well, maybe one last question. You've done work both in industry and academia, and currently you lead a research team at OpenAI, and I think you also have an offer to join Caltech as a professor there. So you must think a lot about the types of projects that are well suited to industry versus the types of projects that are well suited to academia. How would you give different advice to a young researcher working in both domains? Sort of what would be the difference for the advice that you would give to someone to find a promising project in industry versus finding a really promising project in academia?
Yeah. So I think wherever you are, you might be in academia or you might be industry. The most important thing is to work on the most important research questions. And all those constraints are kind of a secondary. For people in academia, I would suggest like do not over-indexing on publishing papers. Instead, trying to focus on projects, trying to drive a project to the finish line.
Yeah.
And try to engage in maybe large-scale open source projects. Try to make more impact using all the resources in academia. And I know in academia, there could be constraints like do not have enough GPUs or do not have enough software engineers to help work on something. But I feel all those difficulties, there are ways to get around them. And the most important thing is which direction to focus on, which research problem is most important for AI. I think the same mindset applies for people in industry as well.
Yeah. Have you heard that Richard Hamming thing where he?
Yes.
Yes. Yeah. I just sort of like the like ordering of that. From my understanding, so we go around and ask people, what do you think the most important problem is in your area? And you would sort of wait for them to answer and you'd sort of think, well, is that what you're working on? And if the answer is no, you sort of immediately.
And then something's wrong, right?
Yeah, exactly. How specifically would you recommend people get around these constraints? Like I'm sort of thinking specifically in a sort of grad student academic setting where, it seems like there's experiments you could run if you had more compute. It seems like the implementation difficulty with some things is too high. Sort of how tactically is it about like sort of finding a version of the research that you can do with less resources? Is it about being scrappy and figuring out some way to convince venture capitalists to give you compute? What is it?
Yeah. So first of all, I fully agree with what Richard Hamming has said. We should focus on the most important problem first. So if someone believes the most important problem can only be solved with lots of GPUs, with a lot of resources, then they should leave academia and join industry. It shouldn't be restricted by where they are. Right? They should focus on what problem they want to solve. And they have the choice to either stay in academia or stay industry. Right? They are not forced to stay in academia or stay in industry. So that's probably the easiest way to get around all the constraints. If you have these constraints in your environment, you can change the environment.
Yeah. Yeah, it's sort of decide first on the higher order bit of what you should be working on, and then that tells you if the right setting for it.
Right.
Amazing. Well, thank you so much for coming in to talk. I really enjoyed this.
Of course, I really enjoyed the discussion with you.
Awesome.